In this video, we're going to talk about chemical kinetics. We're also going to talk about reaction rates and also how to write the rate law expression using the initial rates method. So you might be wondering, what is chemical kinetics? Well, chemical kinetics is the study of reaction rates. It tells us how fast a reaction can occur. So we're concerned with the speed of a reaction, which is quite different than thermodynamics. In thermodynamics, we're concerned if a process is spontaneous or not. Will it occur or will it not occur on its own? A good example is the conversion of diamond to graphite. This is a spontaneous process. The free energy change of the reaction is negative, which tells us that it's spontaneous. However, in real life, if you were to take a piece of diamond, you wouldn't notice any change from diamond to graphite. You can have a piece of diamond for 10 years, it will still look like diamond. And so even though this reaction is energetically favorable according to thermodynamics, the process is so slow that it's not very useful in terms of everyday application. So chemical kinetics would describe how fast this reaction is going. It says basically it's a slow reaction. Thermodynamics basically tells us that this reaction is spontaneous, is energetically favorable. Another example is the combustion of glucose. When glucose reacts with oxygen, it produces carbon dioxide and water. Delta G for this reaction is also negative. So this reaction is spontaneous, is energetically favorable. Energy is released during the combustion of glucose with oxygen. However, if you were to put sugar on a table, it's not going to spontaneously combust. Glucose doesn't react with oxygen very fast at room temperature. So this too is a slow reaction. The activation energy is relatively high. So even though it's spontaneous, it's not a fast reaction unless you heat it up or add a spark to it. Same thing is true with gasoline. Gasoline doesn't always spontaneously combust in air unless you give it a spark or something to get the reaction started. So these chemical reactions at room temperature is relatively slow. So make sure you understand that chemical kinetics deals with how fast a reaction can occur, whereas thermodynamics tells you if a reaction is spontaneous, if it's energetically favorable. Now consider the reaction where A converts to B. So A is the reactant, B is the product. Now, as the reaction proceeds from left to right, the concentration of the reactant will decrease. The concentration of the product will increase. Now, we could describe how fast this reaction is going by measuring the rate of the reaction. The rate of the reaction is going to be equal to the change in the concentration of B divided by the change in time. So the square brackets indicates concentration. So we have the units molarity over some unit of time, like seconds, it could be minutes or hours. So typical unit of rate is molarity per second. It could be molarity per minute and so forth. Now we have a positive sign here because the concentration of B is increasing as the reaction progresses. But we can describe the rate of the chemical reaction with respect to A. It's also equal to the change in the concentration of A divided by the change in time. But we're going to put a negative sign in front. So by putting the negative sign in front, the reaction rate is assumed to have a positive value by definition, because the change in A is negative times another negative, which will make this positive. So for reactants, you're going to have a negative sign if you relate it to the rate of the overall chemical reaction. With products, you're going to have a positive sign. So let's draw some graphs. So if we were to plot the concentration of A with respect to time, the concentration will decrease over time. Now how it decreases depends on the reaction. It can be a straight line or it can be a curved line. But generally speaking, the reactant will decrease in concentration over time. whereas the product, let's use B for example, the product B will increase in concentration over time. Now let's erase a few things. The change in concentration of B divided by the change in time, this is known as the average rate of appearance of B. B is appearing. The concentration of B is increasing. If we wish to calculate the average rate of disappearance of A, it's simply the change in the concentration of A divided by the change in time. So what we would do is we will take the final concentration of B, subtract it by the initial concentration of B, and then divide that by the change in time. That is the time difference between these two concentrations. And the same is true for calculating the average rate of appearance for a reactant A. It would be just the final concentration of A minus the initial concentration over the change in time. Now let's say if we have a reaction where one molecule of A reacts with 2 molecules of B to produce 3 molecules of C and 4 molecules of D. Now we can express the rate of the overall reaction in terms of the change in concentration of A, B, C, or D. And here's how you can do it. So the rate is going to equal negative the change in the concentration of A divided by the change in the concentration of, the change in time. So that's the rate with respect to A. Now what about with respect to B? This is going to be negative change in the concentration of B divided by the change in time. But there's more to it. We need to incorporate the 2. So you need to divide by 2. So it's going to be negative 1/2 times the change in concentration of B over the change in concentration of time. So this is how we can relate the rate of the chemical reaction with respect to the rate in the change of the concentration of B. Now with respect to C, the rate of the chemical reaction is going to equal, this time it's going to be positive since we're dealing with a product. The product increases in concentration. The coefficient is a 3. So instead of 1/2, it's going to be 1/3 times the change in the concentration of C divided by the change in time. Now for D, it's also a product, so it's going to be plus, and then it's going to be 1/4 the change in the concentration of D divided by the change in time. So let's consider an example problem. Let's say that B has an average rate of disappearance of negative 0.5 molarity per second. What is the average rate of appearance of C? And also, what is the rate of the reaction for this example? So let's calculate the average rate of appearance of C, which should be positive. So we're going to start with 0.5 molarity per second, or you can express it as moles per liter per second if you want to. But this is going to be substance B. And we can convert it to substance A. The molar ratio is 2:3. So the molarity ratio, so to speak, will be 2:3. So we could say 1 molarity per second for B, and that's actually 2. The coefficient in front of B is 2. So when the concentration, or rather when the molarity changes by 2 for B every second, the molarity for substance C will change by 3 every second. So we can cancel the unit molarity per second for substance B, and we can get the average rate of appearance for substance C. So it's going to be 0.5 times 3, which is 1.5 divided by 2. So that's going to be positive 0.75 molarity per second for C. Now technically this should be a negative value because B is decreasing, but this too should also be negative because it's still decreasing, and this should be positive. So overall, these two negative signs will cancel, giving us a positive result. So make sure you understand what this means. The average rate of disappearance for substance B is negative 0.5 molarity per second. The average rate of appearance for substance C, 0.75 molarity per second. Now let's put this number here. So we have positive 0.75 molarity per second for C. And we're going to use both numbers to calculate the rate of the chemical reaction. So the rate of the chemical reaction with respect to B is this. It's negative 1/2 times the change in concentration of B divided by the change in time. So this part right here, delta B over delta C, that is the rate of disappearance, or the average rate of disappearance for B, which is this value. So we're going to replace that with negative 0.5 molarity per second. So negative 1/2 times negative 0.5, this is going to be positive 0.25 molarity per second. So notice that the rate of the chemical reaction is going to be equivalent to the rate of the change in concentration of a substance with a coefficient of 1. In the case of A, it would simply be negative 0.25. So the rate of disappearance and the rate of appearance for each species is going to be proportional to the coefficients in front of them. As you can see, C has a change in concentration per change in time that's 3 times the amount relative to A, because the molar ratio is 1:3. Now let's calculate the rate of the chemical reaction, but with respect to C. It's going to be positive, we used in this equation here, 1/3 delta C over delta T. So that's 1/3 times 0.75. So here we have two positive values. The overall rate of the reaction will be positive. And we're going to get the same answer. It's going to be positive 0.25 molarity per second. So I want you to understand how this equation relates to the rate of the chemical reaction. So now you can calculate the rate of the chemical reaction with respect to any of the substances in the reaction. Now let's work on some practice problems. So in this example, we're given a table that shows the concentration of NO with respect to time. Calculate the average rate of disappearance of NO in the first 20 seconds. So what should we do in this problem? To calculate the average rate of a reaction, you need to calculate the change in concentration and divide it by the change in time. So to calculate the average rate of disappearance of NO, it's going to be the change in the concentration of NO, which is the final concentration minus the initial concentration divided by the time difference. So we need to do it for the first 20 seconds. So that's from 0 to 20. The final concentration at 20 seconds is 0.586 moles per liter, which is molarity, minus the initial concentration, which is 0.75. And the time difference is 20 seconds. So 0.586 minus 0.75, that's a change of negative 0.164 divided by 20. And so the average rate of disappearance of NO is negative 8.2 times 10 to the minus 3 molarity per second. So that's the average rate of disappearance. Now let's move on to the next problem. Dinitrogen pentoxide decomposes into nitrogen dioxide and oxygen gas as shown in the equation below. If the average rate of appearance of NO2 is 4.6 times 10 to the minus 3 moles per liter per second, what is the average rate of disappearance of N2O5? So how can we find the answer for this problem? It turns out that the rate of appearance for NO2 is directly related to the rate of disappearance of N2O5 based on the balanced chemical equation. In fact, you can use the molar ratios to get the answer. You simply need to convert it. So let's start with what we're given. 4.6 times 10 to the minus 3, and that is moles of NO2 per liter per second. Now let's convert moles of NO2 to moles of N2O5. Now, for every 4 moles of NO2 that appears or that is produced, 2 moles of N2O5 disappears. Now, you need to understand that the rate of appearance is always positive and the average rate of disappearance is always negative, which means that the concentration of the reactants always decreases and the concentration of the products increases as the reaction moves forward. So the rate of the reaction in terms of reactant should always be negative, and for a product it should be positive. So I'm going to put a negative sign since we're dealing with a reactant. So these units will cancel. And so it's going to be 4.6 multiplied by negative 2 divided by 4. And so the answer is going to be negative 2.3 times 10 to the minus 3 moles of N2O5 per liter per second. So that's how you can calculate the average rate of disappearance of N2O5. Number 3, the graph below shows the concentration of Fe plus 3 with respect to time. Estimate the average rate of disappearance of Fe plus 3 in the first 30 seconds. To calculate the average rate of change from a graph, you need to calculate the slope of the secant line. So we need 2 points. A secant line touches the curve at 2 points. So the slope of this line will give us the average rate of change. Now, if we want to find the instantaneous rate of change, we need to find the slope of a tangent line. And the slope of the tangent line touches the graph at 1 point, as opposed to the secant line which touches it at 2 points. So keep that in mind. So whenever you want to find the slope of a line, it's the change in y divided by the change in x. And in this problem, the change in y values represents the concentration. So it's going to be C2 minus C1. The change in x values is the change in time. And the change in concentration divided by the change in time can give us the rate of disappearance of Fe plus 3. So this is the initial concentration, which we'll call C1, and this is the final concentration, C2. So it's going to be the final concentration, which is about 0.4 minus the initial concentration, which is 1.0, divided by the change in time, which is the first 30 seconds. So 0.4 minus 1, that's negative 0.6 divided by 30, and so it's going to be negative 0.02 m per second, or molarity per second. So that's the average rate of appearance, or rather disappearance, of Fe plus 3. So now let's briefly talk about the rate law expression. This is also known as the differential rate law, which is different from the integrated rate law. The differential rate law shows how the rate of the chemical reaction depends on concentration. The integrated rate law, which is not really covered in this video, it shows how concentration depends on time. So here's a typical rate law expression. In this equation, the rate of the chemical reaction is equal to some rate constant K times the concentration of A, let's say to the first power, times the concentration of B to the second power, times the concentration of C to the third power, times the concentration of D, let's say to the 0 power. When you see a rate law expression, you need to know what this means. The rate of the reaction is first order with respect to A. It's second order with respect to B, third order with respect to C, 0 order with respect to D. So the order for each reactant is simply the exponent associated with that respective reactant. Now, another thing you need to be familiar with is something called the overall order for the reaction. To find this, simply take the sum of all of the exponents. 1 plus 2 plus 3 plus 0 is 6. So we can say that the reaction is 6 order overall. Now, what does it mean when it's first order with respect to A? This means that if we double the concentration of A, the rate of the reaction is going to increase by a factor of 2. And the reason for this is 2 to the first power is 2. If we were to increase A by a factor of 3, the rate of the reaction will increase by a factor of 3. 3 to the first power is 3. Now what about B? What does it mean that it's second order with respect to B? If we were to increase the concentration of B, let's say by a factor of 2, the rate is going to increase by 2 squared. So it's going to increase by 4 because 2 squared is 4. If we were to increase the concentration of B by a factor of 3, the rate is going to increase by a factor of 3 squared. 3 squared, or 3 times 3, is 9. So the rate is going to increase by 9. If we were to increase the concentration of B by a factor of 4, 4 squared is 16. So the rate is going to increase by a factor of 16. So that's what it means when it's second order overall. Any changes in the concentration of B, the changes that the rate will feel will be squared of what the changes that B feels. Now let's focus on C. It's third order with respect to C. So if we increase C by a factor of 2, the rate is going to go up by 2 to the third power. 2 to the third power is 8. So the rate of the reaction will increase by a factor of 8. If we increase the concentration of C by a factor of 3, 3 to the third power is 27. So the rate is going to increase by a factor of 27. I'm giving you a lot of examples because I really want you to understand this concept. Now let's focus on D. It's zero order with respect to D. So if we increase the concentration of D by a factor of 2, what's going to happen to the rate? What would you say? 2 raised to the 0 power is what? Anything raised to the 0 power is 1. So there's not going to be any change for the rate. It doesn't matter how much we change D. Let's say if we were to increase D by a factor of 3, the rate will still not change. There's going to be no change in the rate of the chemical reaction. 3 to the 0 is 1. So the rate of the reaction doesn't depend on a concentration with a 0 order. Let me say that again. The rate of a reaction doesn't depend on a reactant that is 0 order. So in this case, for this particular example, the rate doesn't depend on a concentration of D. If you increase D or if you decrease it, the rate of the chemical reaction will still be the same. So a 0 order reactant has no effect on the rate of the reaction. The one that has the greatest effect is reactant C because it has the highest order. If you double C, the rate will greatly increase by a factor of 8. So C has the greatest effect on the rate of the chemical reaction, but D has no effect on it. Now let's work on some practice problems that involve finding the rate law expression by experiment. So in this problem, we're given a table which shows the concentration of reactants A and B in units of molarity. And we also have the initial rate of the reaction with the units molarity per minute. So how can we determine the rate law expression that fits the experimental data? So first, we need to find the order of the reaction with reactants A and B. So what you want to do is pick two trials in which one reactant is held constant, but the other changes. So if we pick trials 1 and 2, notice that A is held constant in concentration, but the concentration of B doubles. So as B doubles from 0.20 to 0.40, notice that the rate increases by a factor of 4 from 0.4 to 1.6. So you can write this expression: 2 to the what power is equal to 4. We know that 2 squared is 4, so x is 2. This means that it's second order with respect to B. So when we write the rate law expression, let's say for A, we don't know what the order is, so I'm just going to put a y variable. But for B, we know it's second order. So anytime the concentration doubles, and if the rate quadruples, you know it's second order. But if you wish to calculate the two, if you want a step-by-step process, here's what you could do. We can use the formula B2 over B1 raised to the x is equal to R2 over R1. Now, A is constant, so we don't have to worry about A. But for trials 1 and 2, B changes. So that's why we have B in this expression. So B2, or the concentration of B for trial 2, is 0.4. The concentration of B for trial 1 is 0.2. And the rate for trial 1 is 0.4. And the rate for trial 2 is 1.6. So 0.4 divided by 0.2 is 2. And 1.6 divided by 0.4 is 4. Now, if you wish to calculate x, it's going to be log 4 divided by log 2. You just got to take the log of those two numbers. And this number is always going to go on the bottom. This one's going to go on the top. Log 4 divided by log 2 is equal to 2. And so that's how we know it's second order with respect to B. So now let's find the order with respect to A. So notice that if we pick trials 1 and 3, A doubles from 0.20 to 0.40, but B is held constant. And notice what happens to the rate. The rate doubles from 0.4 to 0.8. So since A doubles, we're going to put a 2, and the rate doubles, we put a 2. So 2 is the same as 2 to the first power. So y is equal to 1. So it's first order with respect to A. Now for those of you who want to use the formula, here's what you can do. It's going to be A2 divided by A1 raised to the y, and that equals R2 over R1. But I'm going to change it a little because we use trials 1 and 3, so I'm going to write A3 over A1 raised to the y, and that's equal to R3 over R1. So A3 is 0.4. For trial 1, the concentration of A is 0.2, and that's raised to the y. For trial 3, the rate is 0.8, and for trial 1, it's 0.4. So 0.4 divided by 0.2 is 2, and 0.8 divided by 0.4 is also 2. So therefore, y is going to be log 2 divided by log 2, which is equal to 1. And so that's how we know it's first order with respect to A. So now what is the overall order of the reaction? It's first order with respect to A, second order with respect to B. To calculate the overall order of the reaction, all you have to do is simply add the exponents. So 1 plus 2 is 3. That means that the reaction is third order overall. So this is the rate law expression. This is the answer to part A. Now what about B? Calculate the value of the rate constant. So pick any trial. I'm going to choose trial 1. For trial 1, the rate is 0.4, and A is 0.20 or 0.2, and B is 0.2 as well. So 0.20 squared times 0.2, that's equal to 8 times 10 to the minus 3, or 0.008. So K is going to be 0.4 divided by 8 times 10 to the minus 3. So in this example, K is 50. Now we need to determine the units of K. So in this expression, solve for K. So K is going to be the rate divided by everything on the right except K. So K is equal to the rate divided by A to the first power times B to the second power. And we're given the units of the initial rate. It's molarity times minutes to the minus 1. So let's write that. Molarity to the first power, and then minutes to the negative 1 power. Now A is in molarity, and B is in molarity, but it's squared, so I'm going to write m squared. Now we could cancel m, and I'm going to take this m, move it to the top. So the units of K, you can write it as molarity to the minus 2 times minutes to the negative 1. Now keep in mind that molarity is moles per liter. So you can write molarity as moles to the first power, liters to the negative 1. So if we raise everything to the negative 2, that means we need to multiply every exponent by negative 2. And so what we now have is that molarity to the negative 2 power is moles to the negative 2 times liters to the positive 2. Negative 1 times negative 2 is positive 2. So we could replace m to the negative 2 with moles to the negative 2 times liters to the positive 2. So therefore, we could write the final answer for K like this. So we could say K is equal to 50 times moles to the negative 2 times liters to the positive 2 times minutes to the minus 1. It might be better to put the positive exponent first. So you could say it's 50 liters squared times moles to the minus 2 times minutes to the negative 1. And there's a lot of ways in which you can adjust these units. Now you could write it in terms of positive exponents. You could move the negative exponents to the bottom. So you could say it's 50 liters squared per mole squared times minutes, where these two are in the denominator of the fraction. So now you know how to calculate the value of the rate constant, and you know how to determine the units of the rate constant K. So now, let's focus on part C. What will be the initial rate if the concentration of A is 0.5 moles per liter and B is 0.8 moles per liter? So now we just got to plug it into the equation. So we have the value of K. K is going to be 50, and the units is m to the negative 2, which is basically, you could put that on the bottom, m squared, and then it's minutes on the bottom as well, which is minutes to the minus 1 on top. So that's K, and then the concentration of A is what we have here, 0.5 m, and the concentration of B is 0.8 m squared. So 50 times 0.5 times 0.8 squared will give us a rate of 16. Now m squared will cancel, and so the units for rate will be what we have here, molarity per minute. And so it's 16 molarity per minute, or moles per liter per minute. You can describe it either way. And so that's it for this problem. So now you know how to determine the rate law expression, how to calculate the value of the rate constant, and how to calculate the initial rate given different concentrations.